Today I'm going to be teaching how to use an energy table to solve a conservation of energy problem. So here is the actual problem that we'll be completing, and here's the energy table we'll be using. In the upper left-hand corner, we're going to write the number of the problem. So we're just going to call this problem number 1, and I'm going to go ahead and put a 1 up in this corner. The second thing we're going to do is take a look at how many positions we see this box in. We see it in position A, position B, and finally in position C. So I'm going to go ahead and put those in these boxes here at the top. A, B, and C. So then I take a look at what else is going on. We're just going to go ahead and take just a look at situation A here. In situation A, I see a couple of things. I see the velocity of the box is 0. So I'm going to go ahead to my energy table and go ahead and put that in. Velocity of 0. I see that the height, there is no height shown. So I'm going to assume that that is also 0. And here I have an x value. X value means that there's a spring and it is indeed compressed. So the x value here is 0.56. Okay. Now that I have this, I am able to go ahead and use my equations that I can actually find down here on my piece of paper to solve for the kinetic energy, the gravitational potential energy, and the elastic potential energy. So I'm going to go ahead over to my scrap paper, and I'm going to show you solving for the kinetic energy. So what I have is my base equation states that kinetic energy is equal to 1/2 mv squared and if I go ahead and take a look, I have my mass of my box is on this drawing to be 4 kilograms. So I have 0.5 times 4 kilograms times the velocity, which is 0 meters per second. So if I have that 0.4 times 4 times 0, which is equal to 0, and the unit for energy is joules here. So see, I made a calculation for 0, but if you can see in the future that the calculation ends up being 0, you can just go ahead and put 0 joules right into your box. So here we have 0 joules. If I have no height, then if I were to do the calculation for gravitational potential energy, I would end up with 0 joules again. So the only type of energy I'm going to have here is elastic potential energy. So let's go ahead and do the calculation for that. So I have elastic potential energy, PK, and I'm going to go ahead and put the equation in, which is 1/2 kx squared. K is given over here. K is a spring constant. It's how strong the spring is. So we're going to have 0.5 times 2,000 newtons per meter times 0.56 squared. If you're doing a quick calculation of this, you should get an answer of 314. And again, the units for energy are joules. So we're going to go ahead and pull it out here, 314. And then the last thing we have in this column is the mechanical energy. So we're just going to go ahead and add these up. 0 plus 0 plus 314. Our total mechanical energy is 314. Okay, so we're going to take a look at our picture and see, has there been any loss of friction in between points A and points B? As we can see here, there's no indication of any situation or scenario that would tell us that there is friction. What that would look like is, in a question down here, this would be a patch of friction. Since we don't see that, we can assume that energy has indeed been conserved, and the mechanical energy going from point A to point B is the same exact number. So we can start by filling in 314 in column B. All right. So looking at our box here, we see that it has some velocity, but we do not know what it is. But we can say that there's no x value because the spring is gone now. The spring has already been used, so this is going to be 0. And we also don't have this box at a height at all, so this is also going to be a 0 value. We'll have to figure out what this is in just a minute. So let's take a look at what our calculations would be. If there is no spring, there can be no elastic potential energy, so I'm going to put a 0 here. If there is no height, then there can be no gravitational potential energy, so I'm going to put a 0 here. So what I have left is my kinetic energy. Now, if I try to do a calculation of this, I'd find that I don't have the velocity, so that doesn't help me out. But what I can do is the mechanical energy is kinetic energy plus gravitational potential energy plus elastic potential energy is equal to 314. So we can figure out that all of the energy right now must be kinetic energy. So we're going to put 314 into this box here. 314 joules. And from this, I can go ahead and solve for the velocity. I have to do a little bit of rearranging here, but hey, no problem. So if I rearrange, I'm going to skip that for you. We end up with the velocity is equal to the square root of 2 times kinetic energy divided by the mass. If I go ahead and do a quick calculation, plug in my numbers, figure it out, I'm going to get 12.5. meters per second. So then I take a look at my picture again, and I see, okay, from point B to point C, I don't see a patch of friction at all. So I'm going to go ahead and say mechanical energy is conserved, so the 314 can go from here over to column C. And what's nice is my mechanical energy is conserved in this entire problem. So what I can take a look at here is a situation. I have a velocity, again, of 0. I have a height now, though, of we don't know. That is the actual question that is being asked here. And again, since there's no spring, our compression of a spring that doesn't exist would have to be 0. So I see if I have 0 spring compression, I'm going to have 0 elastic potential energy. If I have 0 velocity, then my kinetic energy is 0. So all of my energy must be gravitational potential energy. So I'm going to take all this 314 joules and place it here. And then I am able to take my equation for gravitational potential energy and solve for the final height. So if I come over here, I have PEG, gravitational potential energy, is equal to mgh. If I solve for h, I would get the gravitational potential energy. Oops. divided by the mass times gravity, and make sure you have that in parentheses when you're calculating, or else the answer will come up incorrect here. And if you're going to go ahead and plug all this in, you should get a final height of 8 meters. So I can come over here and put this into my chart, and I have officially calculated my final answer for the problem. So this is how you would use an energy table to complete a conservation of energy problem. Thanks for listening.